Okay, and for today, I just, again, I want to let you mostly work, but I want to just show you an example or two of how you can apply the squeeze theorem again, right? So we derived yesterday. Oh, and I wanted to, okay, I'll show you one other pretty cool thing. Maybe I'll just let you play with it. I built a Desmos document using the geometric calculator. There's all these cool Desmos calculators now. You should really mess around with these things a little bit. They're pretty amazing. They do good stuff. So I will introduce you to that. But first, let's take a second look at the squeeze theorem, right? So we know, what's that say again? If I've got two functions, f of x and h of x, that bracket a function on some open interval surrounding a, but maybe not including a, then their limits all have to converge to the same value, right? If the limits of f of x and h of x approach the same value as x approaches a, then g would be squeezed to that same value, okay? Give me 1 to 5 on that. Is that all making sense? I said that pretty quickly, but it's what we talked about the other day, okay? And here's the language. You might want to, either in your textbook, and you guys know how to find your textbook, right? You got all that squared away? Either in your textbook or in the published notes, take a look at the squeeze theorem and make sure that makes sense. It's really important that you get used to reading math, because in college you read a lot of math. I mean, we're going to go at least as deep as you'll go next year in your first calculus class. We'll do that in here, but we're going to do it more slowly. And you're going to have to cover a lot more material, a lot more rapidly next year, and so a lot of it is delivered through text. So you got to get used to reading math, and it takes a little practice, but it doesn't take as much as you think. All right, so how could we do something like this? Use the squeeze theorem to find the limit of x times the sine of 1 over x.
Wouldn't it just be x is or less than
as x approaches 0. Say it again.
Wouldn't it just be x is less than or equal to the sine 1 over x, and then, or just x is in both the blanks, right?
No. So ignore this for just a second. Look at this function here. Does anybody want to anticipate what that limit's going to be as x approaches 0? We'll come back to this at the end and show you how you could even, you can know the answer right now. 1 maybe? Nope, it's not 1. We'll see, and then we'll come back and see. In hindsight, which is always 20/20, you can tell me what you think how you could have known the answer from the very beginning. Okay, let's look at it this way. Let's look at just the sine part of this expression. The sine of 1 over x, but I could say the sine of anything, the sine of a dog, is always greater than or equal to the sine of a train is always greater than or equal to sine of anything is always great. What's the output of sine? Always. What's the minimum value of the output of sine?
0.
No. No. The minimum.
An integer.
Yeah, so on a sine function, what's the minimum value that sine can ever output? What's a sine function look like? It just looks like that, doesn't it? So what's the lowest it ever goes? -1. There you go. How about that? -1. So sine of anything, it doesn't matter what you input. The sine output is always going to be greater than or equal to -1. It's always going to be less than or equal to +1. Agreed? Okay, makes sense. For all x not equal to 0, right? We couldn't input 0 there, agreed? Because at 0, that thing oscillates infinitely. We talked about that. Okay, so then if that's true, if I multiply everything through by x, what do we get? Yeah. Okay. And really, I technically need to multiply through by the absolute value of x. How come? Because if x were negative, if I multiplied the inequality by a negative, what would it do? It'd flip the signs, right? We don't want to do that. We want to retain the same, with the same relationship, inequality relationship between all three parts of this compound inequality. So we'll multiply everything through by the absolute value of x. So I could put absolute values around this. Should, probably. Come on. What's this doing? Oh, I see there's a lot. There we go. Yeah, a lot to do there. And so what happens then? So now by the squeeze theorem, we should be able to answer this. Okay? The limit of negative absolute value of x as x approaches 0 is 0, right? The limit of positive absolute value of x as x approaches 0 is 0, right? And because, wouldn't you agree that this blue expression is going to be trapped between the red and the green expressions for all x other than 0? Right? Has to be, right? Because of the nature of sine. So therefore, by the squeeze theorem, the limit of x times 1 over x, times the sine of 1 over x as x approaches 0 has to be 0 also, right? Make sense? Okay? So we could have anticipated this though, right? I think we could have anticipated this based on the behavior of sine, the possible outputs. We could have probably just jumped right to that, couldn't we? Because if we know that the sine of 1 over x is going to oscillate between negative 1 and 1, then we knew that the behavior of this function would have to oscillate between the minimum value would be negative absolute value of x and the maximum value would be positive absolute value of x, right? Okay, and if we look at the original equation, we could have known what was going on here too. As x is approaching 0, not equal to 0, what are we going to get? If we try to evaluate this limit directly, it's going to give us 0 times a number, right? A finite number. What's 0 times any finite number?
Probably 0.
0. Okay? Make sense? Okay. We could have done something, or could do something similar with this. So there's a bunch of ways we could do this one. Any ideas?
You just plug in the 0 for x.
If I plug in 0 for x here, this is going to evaluate to 0 times 1 minus the output of a cosine function. What's the output of a cosine function going to be? Now, x can't equal 0, but for any other number, 1 over x is going to give us back some value to plug into cosine, agreed? Again, cosine is limited, isn't it? Cosine, like sine, is going to oscillate between negative 1 and 1. So I'm going to get 1 minus some finite number times 0. So what's the output going to be? It's going to be 0, isn't it? Right? Okay, how could we show that more rigorously using the squeeze theorem? Very similar. Yeah, we could do it very, very similarly. We could take this whole expression. What would the expression 1 minus cosine of anything have to oscillate between?
Oh, 2 and 0.
0 and 2, right? Because cosine is going to oscillate between negative 1 and 1. And if we're subtracting that from 1, this would oscillate between 0 and 2. So we could do it that way, right? We could do it that way. Or we could just maybe focus on just a way that's more similar would be to split this up into separate limits. This is the limit, if I distribute the x, this is the limit of x as x approaches 0 minus the limit of x cosine 1 over x as x approaches 0, right? Does that make sense? Okay. Isn't this problem right here essentially identical to the one we just did? Right? Limit of x cosine of, I mean, that's the same thing, right? Cosine and sine, they're just shifted a little bit. The curves are just shifted a little bit, but in the limits, we're going to get the same values, aren't we? Right? Everybody see that? We're going to treat them exactly the same. Cosine function is still going to be, replace sine with cosine. The cosine function is still trapped between -1 and 1. So we could apply exactly the same logic. I'm just going to do this quickly so you guys can work a little bit. And if I take the limit of 0 times a non-zero finite number, I'm going to get 0 out of that, just like I did before, right? And so what's the outcome then? Well, we just get 0 minus 0 equals 0. Okay? Make sense? All right. So here's I built this thing, so I at least have to show it to you because I spent all this time building it. So if you look at, this was kind of fun. I'd never used this before. This is kind of cool stuff. A little nerdy, but fun. If we look at our example from yesterday, that looks pretty familiar, doesn't it? So we've got a circle of radius 1. And let's start off with that rectangle. Or sorry, that triangle, right? And I can drag this point around. That's going to define some angle in radians, right? There's the output of that angle. And if we calculate the area of this guy, it's right there. The area is 0.218, blah, 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 blah. Okay? So let's look at that sector. Okay, if I look at that sector right there, I can calculate the area of that sector. That's going to be, let's see, where is the area of that sector? It's right here, right? That's just the formula for area. 1/2 times the angle times the radius squared. Radius is 1 in this case, right? Radius is 1. And so look, I get another area, which notice it's slightly bigger than the area of that previous blue triangle. Okay? Now finally, let's look at something like that red triangle. Well, that red triangle, its area, if I drag this thing around, notice it changes, but its area always stays a little bit bigger than the sector, which is a little bit bigger than the inner triangle. And as I let this thing approach 0, what happens? They all go to 0, right? And so that inner sector is pulled to 0. If you look at the trig values, I want you to notice something kind of cool. And I'll publish a link to this, and you guys can just mess around with this if you want to. So here are, if you look at the proof we did yesterday, that looks familiar, right? Those are the areas. Notice they're exactly the same. The area of the blue triangle, let me go highlight that again. There it is. Make this a little bigger. The blue triangle. Notice that that is exactly equal to sine of theta. In this case, it's A1 is the angle, but sine of the angle divided by 2. Look, that is the area, right? The area of the sector simplifies to just theta over 2, right? And the area of the red triangle simplifies to tangent theta over 2, just like we had yesterday. And then finally, if you look at the final trig values that we came up with, we said, well, sine theta over theta was trapped between 1 and cosine theta. And look what happens. As we drag this point down towards 0, notice that cosine is a little bit less than sine. Cosine theta is a little less than sine theta over theta, which is a little less than 1. But as theta approaches 0, they're all getting dragged to 1, right? And so there's, by the squeeze theorem, the limit of sine theta over theta is 1. I did that pretty fast. But again, I will publish a link to that, and I will just email it to you. How about? What I'm gonna do, I tell you what, I'm just gonna make a document that has links to every cool Desmos thing that we use, and then you can always just access them all. I'll just update that. I'll put it in Google Classroom. Okay? How about it?
Desmos stuff.
Yeah, what was
Yeah.
that function that broke Desmos?
Oh, like that weird wavy?
Yeah, what was the function that broke Desmos? We broke it the other day. Oh, I know what it was. It was when we tried to get, what was it?
There was that one where it had like really heavy lines on it, where if you zoomed in, it just kept having really heavy lines that were super close together.
Yeah. We were taking a limit, right? And we were trying to just get, we let something, I can't remember, what the heck was it? We let something get really big, I think. We let n get really big. Or no, we let it get really close. I know what we did. We let it get really close to like 0 or 1 or something. And when I picked a number that was way out there, it broke Desmos. It couldn't handle all the decimal places. Yes.